Hi, my name is Weisheng Zhao. I come from First Beijing Institute, Beihang University. Today it's my great pleasure to have this opportunity to present our work at the first international symposium on AI electronics at Tohoto University. I will present our thinking about using MRAM for AI electronics. My talk will include three parts. The first is about why we need MRAM for AI electronics. The second part, I will introduce our recent progress on the new switching method and its perspective for AI electronics. First, I will introduce briefly MRAM. As I noticed, the audience may be not that familiar with MRAM. The basic of MRAM is coming from the using of spin property of electron to build up electronics. While with the traditional spintronic devices is the magnetic junction, which present 0 or 1, showing high and low resistance. The first generation of MRAM is based on field-induced magnet switching, and it has been widely used in our life, such as airplane and satellite. Based on this new technology, these systems have obtained the best trade-off between the radiation hardness and the performance. However, the major drawback of this system is its power dissipation. Due to the using of the magnetic field for the switching, its power efficiency is very low. We need at least 100 picojoule per bit for switching. Therefore, from 1996, Dr. Slonsavsky from IBM was proposing the spin transfer torque, which used only a current to switch the magneton junction, and the power dissipation can be reduced down to 1 picojoule per bit. During this development, Professor Ono did a breakthrough and proposed the using of interfacial perpendicular magnetic anisotropy to combine with the spin transfer torque mechanism. In this structure, you can see the data is stored in the interfacial perpendicular magnetic anisotropy, and the switching current is against the spin momentum direction of the data. So this is a perfect combination to enable the second generation of the MRAM. We named spin transfer torque MRAM, STT-MRAM. So for the first time, spin transfer torque STT-MRAM provides the perspective over resistive RAM and phase change memory, 1 nanosecond here for the switching, and 1 picojoule for each bit switching. The fast speed and ultra low power enable its application for embedded solution and computing system. So for the first time, you can see the after 20-year R&D, we can find that the embedded MRAM has been commercialized by Samsung, TSMC, and GlobalFoundries. For the academic people like my group, we are focusing on the reading optimization of STT-MRAM devices to enlarge the on-off ratio. So for the resistance, In this case, so we realized the world record on this reading performance by using atom-thick tungsten to achieve this high R-on R-off ratio. The reliability and the switching performance are continuously optimizing, as you can see from the program of IEDM last year. A lot of progress has been done on STT-MRAM. So you can see Intel, Samsung, GlobalFoundries, and the proposed optimizations. Thanks to this embedded MRAM, new AI electronic can be expected. This is an example of using MRAM to store the weight of learning. The learning is proceed in the cloud server, and the calculated weight will be sent to the AI chip in the module of MRAM. We expect to have a large density of memory to bring high precision weight, which would lead to higher intelligence. Therefore, STT-MRAM has much more advantage over SRAM on the density. So in the case of this AI chip, we have 40 megabyte STT-MRAM. It's impossible to realize with only SRAM. So this is a good example of MRAM for AI chips. However, we can notice that the computing unit should be still SRAM, as we need ultra-fast speed to process the data. In this case, STT-MRAM is not that fast than SRAM. I can give you a second example of using STT-MRAM devices for AI chips. When we operate the spin transfer torque mechanism, you can see a current passing through magnetic internal junction. Its behavior are intrinsically stochastic, as shown in this figure, which is very similar to the behavior of our brain. By integrating this probability and the rate in the computing, we could expect energy efficient intelligence. There are many other examples of using MRAM for AI electronics in this very recent overview paper published in Nature Electronics. I recommend you to read this paper if you are interested on the other implementation of AI chip by using spin STT-MRAM. However, there is a limitation related to STT-MRAM. Its lifetime. So in this table from GlobalFoundries, you can see endurance is the lifetime of the chip. Here, there are two types of MRAM. MRAM-F is that to replace flash memory, and S is to replace SRAM. So you can see that the endurance has large difference between SRAM and STT-MRAM. This is why in the AI electronics, we can use STT-MRAM to store its weight, but we cannot use STT-MRAM to store the data because its lifetime is a limitation. So this is another example of STT-MRAM realized by Intel recently. You can see its write endurance is also very limited. So it's a common limitation of STT-MRAM that we can use it to store the weight of AI chips, but we cannot use it to store the data. What's the limitation? So one of the reasons is we use the same path to read its state and to write its state. In this case, we need a number of challenge, because when we want to write it correctly, the voltage should be high. In this case, this current will be approaching to the breakdown current. IBD is the breakdown current. So when we use the low current to read it, it's approaching to the current to write it. In this case, there are two types of errors. The read disturbance. The read current will disturb its state, and the write endurance error. So this is why we cannot use STT-MRAM for fast to combine the fast speed and the large lifetime. A number of methods and new physics have been proposed to replace STT-MRAM. So one of them is spin orbit MRAM. So in this case, we use the spin orbit mechanism to switch the device. So the major difference here is it's a 3-terminal devices. We send a current not passing through the magneton junction as on the bottom to passing through these devices. This is very similar to the transistor. It's a 3-terminal devices. In this case, we separate the read and the write path, and then we can switch it faster. However, the error penalty due to the 3-terminal. So this is one of the limitations. And another problem is we need a magnetic field to switch this type of magneton junction. And so it's still, it can overcome the problem lifetime, but it cannot resolve the problem of using magnetic field. So in this case, many switching recent work are focusing on how to realize the SOT spin orbit torque mechanism without magnetic field. So one of the work has been proposed by Professor Fukami from Tohoku University. One solution is to use wedge-shaped devices like that, but we cannot use it for the practical chip fabrication. Professor Fukami proposed AFM to realize the spin Hall effect for the switching, but we cannot use this device, this new material to realize magneton junction. So up to now, the field-free switching induced by electric field or interlayer exchange coupling has not been realized in MTJ system. So very recently, IMEC from Belgium proposed to integrate a cobalt layer to generate a magnetic field, but this is bring other issue. Density is limited by the cobalt layer on top of the magneton junction, and the thermal stability under a permanent magnetic field will be another issue. SOT is for the magneton junction switching, and MTJ is reading through a small STT current. So if it's possible to realize devices to combine spin transfer torque mechanism and spin orbit torque mechanism, so this is a question that and a challenge that we want to realize. So based on this background, I propose this solution to combine STT spin transfer torque and SOT spin orbit torque. So this is a combination of two electrical current switching method. But at the time, it's just an idea. Now I will present the experimental results. First, I want to show our thinking about the future development of MRAM. So STT PMTJ based on the interfacial perpendicular magnetic anisotropy. This is actually the mainstream MTJ. As I mentioned, that we want to go to 3 terminal to enlarge, increase its lifetime. We should go to 3 terminal. In this case, we can combine the 2 interface for the switching. So the current comes from the top to the bottom, and the current, another spin current from the bottom. In this case, 2 interfaces have been switched, and the efficiency can be enlarged. This is very similar to the development of FinFET. Actually, the mainstream transistor used in our mobile phone. So you can see that this is a single interface, and this is a 2 interface. This is a single interface in the STT MTJ device, and this is a 2 interface. The first step is to combine spin transfer torque and spin orbit torque, and the next step could be spin orbit torque combined with VCMA, so voltage controlled magnetic anisotropy. Both these 2 devices have 2 interfaces for the switching. So this is very similar to the roadmap of GlobalFoundries. As you can see, both 2 devices has been included in the roadmap of GlobalFoundries, and for these devices, it's invented by our group and realized 2 years ago by the joint group of Weisheng University and Qualcomm. And for the next generation to combine SOT plus VCMA, so it's proposed firstly by Toshiba and realized by the joint group between Weisheng University and UCLA. So as I mentioned, that this development is very similar to the development of 3D FinFET from 1 interface to the 2 interface. And by using this method, the energy efficiency could be higher, and the switching per bit could be from 1 picojoule to 0.01 picojoule, so 100 times lower than the previous solution. And we can completely overcome the lifetime challenge. So here, I will show you some experimental results. So this is the device. As you can see that it's a 4-layer system. This is electrode where we can generate spin orbit torque mechanism to generate a spin current for the switching of these devices. And this is another interface where we can inject the STT current, and they play in the at the same time here to make the switching. In order to validate these devices, first we show here if there are no SOT current, only one interface. So this is a conventional STT curve. You can see that the switching is based on the electrical current from bottom to the from the top to the bottom, and we try also only the spin orbit torque without STT interaction. In this case, we need a magnetic field to realize this SOT switching. So in order to understand what's the property of spin orbit torque, we did the measurement of SOT effective field and to measure its spin Hall angle. In this case, we can find that it's very similar to the value shown in the previous work. So finally, we can show this figure. In this figure, you can see the x-axis is the spin STT current density, and the y-axis is the SOT current density. As you can see, if the STT current is very large, here, the SOT can be very low. On the contrary, if the STT current is very low, the SOT current is very high. So this shows the perfect combination of the joint effect. So we tried different device sizes, and you can see that this combination and the interaction is very reproducible for different devices and with different size. Here this is 60 nanometer, and this is 100 nanometer, 150 nanometer. We tried also different temperature. As you can see, when it's 300K and with 13K, this interaction and combination effect reproduce very well. And we tried also the different pulse duration. Here you can see from 100 microsecond to 10 microsecond. This combination is very reproducible. In this case, we tried also if we sent two terminal device current. So we send just current passing through the MTJ. You can see that when we enlarge the SOT channel, its current density change. This confirm the contribution of SOT mechanism from the bottom electrode. So this is very similar to the work shown in this Nature Electronic paper published just some months ago. So both confirm the contribution of SOT contribution from the bottom electrode. So in order to investigate what's the contribution of physics behind all this interaction between the two interfaces, so we did this experimental the theoretical and study. This is the conventional calculation to get the switching of magnetization. Here we propose two terms. beyond the STT term. So we add the DL, the damping-like torque term of spin orbit torque mechanism. And here is the field-like torque term of SOT contribution. Previous models did not include the field-like torque of SOT. So we propose this new equation in our work that for the switching of the mechanism, we need STT, SOT contribution. And for the STT, the major contribution comes from the damping-like torque. But for the SOT, the major contribution from the field-like torque. So this is the contribution. As you can see that when we enlarge this term, we can reduce greatly the switching current of the spin orbit torque mechanism. At last, we can predict the using of two mechanisms, STT plus SOT, to realize the ultra low power. We can expect around 200 femtorule if we can shrink the device from 60 nanometer down to 10 nanometer. So this is the first step that we can use this interaction between two mechanisms to obtain ultra low power and improved lifetime. So here the energy per bit is from 1 picojoule to 200 femtorule. So how to use these devices? This is an example of using this mechanism to realize the logic. Here we show this is an example experimental work. We can realize a logic, nor or all logic realized by SOT plus STT. So in this case, if we implement this logic, so the input could be STT and another input is SOT. The output is the combination of these two effects. So we can realize also XOR logic, which is the fundamental logic block to realize AI electronics. So let's go back to the roadmap of MRAM from our point of view. If we want to continue to scaling down the MRAM devices, we need to use voltage control magnetic anisotropy. In this case, the power efficiency could be higher. So this is not a new concept. 3 years ago, Toshiba has proposed this mechanism. They proposed to use implant magnetic tunnel junction, and when we apply a voltage on the magnetic tunnel junction, the current density can be lowered 2 or 3 times. In this case, the power efficiency can be improved. So this is for implant magnetic tunnel junction. But for implant, as we don't need the magnetic field for the SOT mechanism, but as mentioned before, Professor Ono proposed interfacial perpendicular magnetic anisotropy to enlarge the density. So implant MTJ cannot realize higher density. So this is a key issue of this proposal from Toshiba. So how to realize perpendicular MTJ with the SOT plus VCMA? So this is our motivation. So as mentioned that Professor Ono Fukami proposed to use EFM to realize SOT mechanism. So we want to use the similar material structure. By using EFM, we can generate exchange bias, which can help to eliminate the required magnetic field for the perpendicular MTJ. So this is experimental demonstration that EFM is indeed efficient method to eliminate the required magnetic field for the field-free switching through SOT. So by combining these two proposals, so we proposed this structure. So the SOT channel bottom from the bottom electrode is EFM, which can create exchange bias EB to assist the SOT switching. In this case, we don't need external field. And here we generate SOT. Here we apply the voltage control. And we have a collaboration with UCLA group, which provides the support on the VCMA measurement. Again, this is two interface switching. So first we realize these devices, two devices, with one SOT channel here, and we measure the switching result here. This is our structure. So in order to compare with the conventional SOT structure, tantalum cobalt aerobond MGO, the EFM SOT channel, we can realize field-free switching. So this is the clear, evident experiments to show the field-free switching with this structure, and this is interfacial PMA structure. So here we show that when we send the different pulses, we can switch the devices with repeatable pulses. When a positive, we can switch to this state, and negative, we can switch it back to another state. After the measurement of voltage control magnetic anisotropy, we can get this value. So this value represents the capability to realize voltage control on these devices. So this is 35 femtojoule per VM. It's comparable to the tantalum-based films. So this is the structure, the curve to show the modulation of the interfacial perpendicular magnetic anisotropy. After that, we first calculate this combination with the magnetic simulation. You can see that when we use 0.6 watt, the GC can be reduced to 30 milliampere centimeter square. So this is the voltage 0. You can see that we need around 60 milliampere to switch the devices. So if we apply 1.5 volt, the GC can be lowered 10 times lower than this configuration. So the efficiency of using VCMA is very, very important. Finally, we perform the experimental measurement. This is the switching when we use 0 voltage, and this is 0.6 voltage. The current density is reduced by more than 50%. So if we compare the simulation and the experimental results, you can see that the trends is very similar, and the combination in the two interface for the switching is very efficient. And then we can propose this structure to overcome the problem of 3 terminal. So we can see if we share this SOT channel, because it's passed through the board of the devices. In this case, we can consider it's 2-point X terminal, could be 2.1 terminal if we put many magneton junction on AFM electrodes. Low power can be realized due thanks to the voltage control, and high density can be obtained as the several MTJ can share only 2 transistors. After that, we can perform the simulation, circuit simulation, combine CMOS and MTJ. The power deficient consumption is around 6 femtojoule per bit. So in this case, we can reduce the power dissipation per bit from 200 femtojoule to 6 femtojoule based on the two interface switching from voltage assistance and plus SOT. So what's the perspective using this two interface and two switching mechanism? So we use a new switching mechanism. I called it toggle spin torque. Toggle means the switching can be modulated by these two methods. Spin torques, there are two. Every time there are two switching mechanisms used in these devices. Again, this is the roadmap of this MRAM from our point of view. So why we use toggle mechanism? So first, let's see the first generation of MRAM. In this case, we use two current which generate the joint magnetic field. So these two currents, we use the toggle mechanism. So we send firstly one current, and then after one pulse, so one duration, we send the second current to generate interplay of two currents generating one magnetic field, and then we eliminate another one, and at the last we eliminate all the two currents. So this method has obvious advantage. So one is we can eliminate all this term, because as I showed in the SOT channel, we send the current to a number of MTJ. If we don't use this toggle mechanism, there could be some disturb. We will send the shared SOT switching. So this mechanism can help to overcome this issue. So let's see the example of using STT plus SOT. Firstly, we need to send the SOT. So in this case, we put all the magnetization from perpendicular to implant, and then we send to these two current in at the same time, and we switch it from the this direction to this direction, and then we eliminate the SOT, and then the switching will go another direction. So this could be very power efficient from the point of view to benefit the maximum switching efficiency of the two switching mechanism. So let's see the results. So by using this toggle mechanism, we can control the switching probability very well from this current density to this current density. As you can see, the ST current density can be much lowered, and when we can tune the pulse difference between these two current density to switch to modulate its switching probability to get the best result. So this is a very important mechanism to enable the toggle spin torque switching mechanism plus NAND flash structure to share this SOT electrodes. So this is also inspired from the transistor development. As you can see, this is a multi-gate transistor for FinFET to get the maximum error efficiency, while we can control it with high readability. So this is some results that we can show that when we send the SOT current, we can switch here, and in this case, this device will not be disturbed. On the contrary, if we want to switch these devices, we will not touch this device. So this is very similar idea proposed by Toshiba some years ago, but we can compare our difference. We use TST toggle spin torque MRAM, and we use PMA with STT plus SOT, and the group of Toshiba use VOCSM implant magnetization and VCMA plus SOT. So this is why they get this paper, but we obtain this patents to protect our invention, and this could be important to get higher density and low power. There is a number of advantage for the circuit level advantage. We can larger read this disturb margin, and this is become much easier for the circuit design. So finally, we can get this conclusion. So the toggle spin torque MRAM can get 1 nanosecond switching speed and 1 gigabit devices. So this is finally we propose a memory MRAM possible to replace SRAM for AI electronics. So my conclusion is that spin torque joint force in a memory device. This is some word from Nature Electronics. I think this combination is a good way to realize low power and high density memory. And this is some requirement for AI electronics. Larger memory bring larger, bring smarter intelligence. Low power bring long lifetime, and like our brains, that some small energy can work during long time. So this is not finished. We can continue to reduce the power. So as mentioned, that by using this our proposal, the switching per bit can be reduced from 1 picorule to 200 femtorule, from 200 picorule to 6 femtorule. If we can use the 2D electron gas, so the new mature devices, we can down switching per bit down to femtojoule. So this is another perspective to use MRAM for AI electronics. So if you are interested, you can see this overview paper that I write recently in Nature Electronics. So thank you very much for attention. The question and comment are welcome.